Our talk is titled Blue Devil Wisp, Expanding the Frontiers of Passive RFID Physical Layer. And in this talk, we're going to report about a couple of different ways that we're using RFID at Duke in different applications, and then also get into a particular hardware platform that we've designed that we call the Blue Devil Wisp. As Josh mentioned, the idea of using Wisp as a generic term is something we've embraced. And I'd like to acknowledge NSF, HHMI, and Willow Garage for funding that has led to this work. So at Duke, we've been working in a couple of different application areas for RFID, primarily in robotics and biomedical instrumentation. And in my group, we've been working primarily to optimize sensing, computing, and actuation in this energy harvested context. And that involves both optimizing the physical layer to harvest as much energy as possible, as well as including on-chip sensors or actuators, and working in tag localization and RFID-aided perception for robotics. And I've given a couple of photos of some recent research. In the lower left, you can see a dragonfly, which is a 300 milligram class insect, and it's carrying a 70 or 80 milligram RFID tag, which is attached to its abdomen with beeswax. And we're using the same tracking system that we use in the robotic context to track the dragonflies. In the next generation of our ASIC work, we're expecting to do some biotelemetry from the dragonflies while in flight. So there's a combination of optical and RFID tracking, as well as RFID-based telemetry of EMG and EEG from the dragonfly. And in the right-hand side, you can see a robot that's handing a tagged object to a person, and that's work in collaboration with researchers at Georgia Tech in the Healthcare Robotics Lab. And we're working on using tags to aid machine perception. In other words, fusing data from RFID with laser rangefinders and with optical cameras to give the benefits of RFID, which are the unique identity with virtually zero false positive rate to the machine perception. We've developed a lot of custom hardware to do this. We've developed in particular an array processor for receiving signals from multiple antennas. It's basically a special kind of reader with multiple antennas on it. And the objective there is to use the array processor for localization of tags. You can see a 6-antenna array mounted on a robot platform on the right-hand side. And then there's a bunch of custom hardware here and some HP lab equipment and a PC that's not shown that's actually doing the array processing. Here's some actual measured data from a real environment. The object with the several antennas on it there is the robot, and then we're localizing using a particle filter the tag, which is magenta. And then these two kind of greenish objects are lasers, which are using for ground truth data. So as the robot moves around, our particle filter tracks the location of the RFID tag, even in the presence of multipath in a real world environment. And you can see the gray outline on the outside is the laser hitting the outside of the environment. So that's our boundaries of the room in that case. We published some work on this last year at IROS, and in a typical 10 meter by 10 meter room, we've been achieving localization accuracies of somewhere around half a meter, including the effects of multipath. So in that work, we included the effect of multipath in our model, and we're able to improve our results compared to a line of sight model as well. So that's what we're doing with RFID in general. And I'd like to talk a little bit now about a particular platform that we've been using that is Wisp-like. And that's the Blue Devil Wisp. And in this design exercise, we're basically exploring the Wisp design space. We're adding an actuation component, which is something that the Wisp doesn't have currently beyond its LEDs. The Wisp is currently a sensor and a local computation. In other words, it has input, but it doesn't have human output beyond the LEDs. We are adding a piezo speaker and then hopefully soon a piezo motor to the Blue Devil Wisp to enable both human I/O as well as motion of the tag under the power of the reader. In order to deal with moving tags, we've also worked on an omnidirectional antenna that's planar, and I'll have Stuart will be talking a little bit about that design. We've also been working on improving the backscatter communication link by using multi-state modulation. So using 4-QAM passive backscatter modulation, which is something that Stuart will explain as well. And then last, and this is perhaps one of the more exciting things, we've been working on a companion chip for the MSP430 microcontroller that implements all of the RF circuitry of the WISP on a single die. So on a die that's 1.5 millimeters on a side, we can implement the power harvesting as well as the modulation and demodulation that's implemented in the WISP circuit board to shrink that circuit board down to something that's a couple millimeters on a side. And in doing this, we're really balancing many things at the same time in the design space, including the design of the antenna. As Josh and Alanson mentioned before, there's a complex bit of optimization to do in the power harvester design. And then we're also looking at optimizing the power consumption of the logic and the microcontroller as well. Just to motivate this particular work, which is the work that's been funding Stuart for the past several months, we have an NSF-sponsored project in construction site safety, and we're using RFID on worker hard hats to track workers with respect to heavy construction equipment, and also to alert workers when they are in proximity to a piece of heavy equipment that could hurt them. And in that sense, we've designed this thing we're calling the Blue Devil WISP, which has a warning beeper on it that is powered by the field. And in that case, we need to have passive operation. Oh, I'm holding the antenna, my finger here. We need to have passive operation for very long lifetime. In a safety application, you don't want to be hampered by a battery running out at an inopportune moment. And that's a tremendous benefit of passive operation, is that you have virtually unlimited lifetime unless the tag is mechanically damaged. So this is the first prototype of the Blue Devil WISP, and as you could hear, it has a beeper that is powered by the field. And the idea is to mount this device in the top of or empty space in a hard hat, and I'm right on the edge of the read range. Over here it works, over here it doesn't work. To mount that in the open space above a person's hard hat and use the beeper to alert them of a hazard when one is impending. And in order to do that, we need an omnidirectional antenna. So we've developed a rotation invariant antenna that works in this plane, anywhere in this plane. So if I'm on the edge of the read range, it doesn't work. And we're trying to do that in a reduced size, so we've designed a reduced size antenna for that. And I'll let Stuart speak about the next details of that design.
Excuse me. Okay, so like Matt said, we are designing the omnidirectional antenna because with a standard dipole that most any RFID application uses has a very sharp null when you are rotated away from the optimal orientation, and that's shown in the green part of this graph. So our goal was to be able to operate in the optimal orientation as well as the non-optimal. And we designed two antennas. The one that was demonstrated, we have just another standard dipole and measured those. We wanted to integrate this into the PCB board because eventually we want to be able to have just one component with the ASIC that we've set inside the hard hat. And with that, we have a physical size constraint of the hard hat of a person's head. We also want to integrate our impedance of the antenna into our matching network so that we can match that to our load, which again affects our power transfer and the operating distance. And we also want to have, of course, be able to operate over a full bandwidth of the full 900 megahertz ISM spectrum that we're working with. And these graphs that we have are in plane, so we're looking at the XY plane of the antenna, so it's generally rotation independent. So a key component of any RFID tag, any passive system, is the power harvesting, or power harvesting like we discussed. Well, this is a plot showing the Friz transmission model, or just the standard system. But the measured data, you can see that have the spikes was taken in an indoor lab environment. Not really a problem, but an issue in indoor environment is the effect of